Alright students, if I mention the word copper, what comes to your mind? Is it something like this? Aiyo, call yourself a physics student. As an A-level student, when we mention copper, this should come to your mind. For example, this rod here, length L, is subjected to a copper. So a copper consists of two forces that are of the same magnitude. They're exactly the same in magnitude, but they are exactly opposite in directions. There's nothing lovey-lovey about them. In fact, there must always be a separation between them. So what does a copper do? Since they are opposite in directions and same in magnitude, they will always contribute a net force of 0. So a copper never produces any translational effect. But I think it's quite obvious that this copper is going to produce a clockwise moment. So a copper will always produce a rotational effect. So what's the magnitude of the turning effect? So the magnitude of the copper you can calculate by just summing up the moments contributed by each of the force. If you take moments about the center of the rod, then this force will contribute a clockwise moment of F times half L. This force is also contributing a clockwise moment, also F times half L. So in total is F times L. Actually, you don't have to calculate the moments about this point. You can calculate it about any point. For example, if you calculate about this point, then this force will contribute a clockwise moment of F times L. But this force contributes 0 moment. So the total is still F times L. And you can evaluate the moments about this point here also. It will again turn out to be F times L. In fact, if you want, you can evaluate the moments about this point, or this point, or this point, or this point. You will always arrive at the answer F times L. That's because a copper always results in a net force of 0. So when net force is 0, you can evaluate moment about any point and still get the same answer. So the conclusion is this: when you have a copper, the magnitude of the copper, you can just take one of the force times the perpendicular separation between them. Yeah? So to check whether you have understood, look at this diagram here. So this rod of length L is subjected to a copper. So what is the magnitude of the copper? So this time around, the force is not perpendicular to the rod, yeah? So the perpendicular distance between these two forces is not L, it is actually this distance, which if you consider this right-angled triangle, is just L sine theta. So the magnitude of the copper is F times L sine theta. Get it? So just take one of the force, multiply with the perpendicular distance between the two of them. Another way is to resolve the forces into components perpendicular to the rod and parallel to the rod. We can ignore the copper formed by the parallel components because, there's no separation between them. As I said earlier, right, there must be a separation between the two forces. So we only consider the perpendicular components. So it's F sine theta times L. Right? So the magnitude of the copper is F sine theta times L, which is of course the same as F times L sine theta. Alright, so that's what a copper is all about. Ta-ta!